nice to kind of, thank you. It's really nice to be able to talk about some of the work that I've been doing. So what I'm particularly talking about here, as you said, I work with a range of different things to do with ice cores, but particularly for this seminar series, I'm trying to focus on the work that relates to sea level rise. So I'm going to start, let's change that. So kind of giving a bit of an overview of what I would like to talk about is I'm going to go over the surface mass balance reconstructions during the 20th century. And I'm aware I've actually seen this presented a couple of times in other people's talks, which is great. So forgive me if you feel like you've seen this lots of times before, but I'm just going to go over and add perhaps a little bit of a personal spin on how that story came about and some of the uses of that reconstruction. Then I'm going to touch on really how we still need to understand a bit what's going on and what's driving the variability in the snowfall. And the final part of the talk is really what else can ice cores do for the community and what else can they tell us about sea level rise. So I'm going to start with the real basics. Apologies for everybody, but we all know that Antarctic mass balance it's about what's going in as snowfall and what's coming out as melt. And so there's been generally a lot of focus on what's coming out as melt, and that is a direct contribution to sea level. But also the snowfall itself, as you'll see through this talk, is a pretty important factor as well. And also, again, just the basic physics of Antarctic snowfall, showing here an output from the RACMO model, is that snowfall has a regional pattern in that it's much higher snowfall around the coast, and particularly around these orographic barriers, so the Antarctic Peninsula, shown here in these sort of yellow colours, where we get an awful lot of snowfall. And this is just adding my kind of, I can testify that there is an awful lot of snowfall in the Antarctic Peninsula from a very personal perspective. So my first postdoc at MASS back in 2006, I was fortunate enough to go to Antarctica with the aim of retrieving an ice core. And we were specifically looking, this was working with Gareth Marshall, and we were specifically looking at reconstructing the southern annular mode. But when we got to the site that we'd carefully selected, the first job was trying to find the weather station, which had been put out the year before on a 4-meter mast with a big flag on the top. So it should have been easy for us to locate our site. But when we got there was no sign of it at all. And so we actually had to drag the GPR around and then try and locate it. And I did quite a good job of locating it because our first shovel in through the snow went straight through the top of the wind vane. But this is just kind of demonstrating that although we knew this region was high snow accumulation, it wasn't really until we got there that, 4 meters in a year seemed a huge amount. And as you'll see, involved an awful lot of digging. So the aim, as I said, for this Gomez record that we were bringing back, we drilled 150 meters of ice and we wanted to get the snow accumulation record. And I'm aware that lots of people on here are going to be very familiar with maybe with ice cores or the snow accumulation, or perhaps use the database. But I think it's quite useful sometimes to just go back and touch on actually how we get this record, really with an aim of kind of bearing in mind some of the uncertainties and maybe some of the errors, or perhaps in a more positive light, maybe some of the areas where we need to still work together as a community to get things better. But the way that we get the snow accumulation record, we take advantage of the fact that lots of chemical species are deposited on the ice sheet and they have a seasonal pattern, a seasonal signal. And so the ones that I'm showing here in the blue, this is hydrogen peroxide. And this is a fantastic species because it's a photochemical species. So it peaks during the summer solstice when it's 24 hours of sunlight, and then it switches off to baseline during the polar night. So we know pretty much when it's going to spike is, can almost assign this down to the 31st of December. And then in calculating the snow accumulation, it's literally the distance between these two peaks. But the other thing that we also have on here is the red line. This is the stable water isotopes, and this is quite a traditional proxy within ice core research as a proxy for past surface temperature. So in this approach, we're taking advantage of the seasonal variability in temperature and using those as markers. But what I just wanted to highlight is that this is from the Gomez ice core. It's quite far down. It's between 90 and 95 meters. But actually, there's a considerable offset between if we were using the dating approach based on the hydrogen peroxide and if we were using it based on the isotopes. And so there's an offset just on these years of around about 3 months. And for the sort of beady-eyed among you will notice that actually this offset isn't a continual offset. It's got quite a lot of variability in there. So it's just highlighting that actually the way that we calculate snow accumulation is essentially the distance between these peaks, but there's also going to be quite a bit of variability in assigning these peaks. So just kind of highlighting really that there's some unknowns and some things we still need to work on within this. And importantly for the hydrogen peroxide, although it's fantastic at the high accumulation sites, it's really not suitable at all at any of the inland sites where the signal disappears within the top few meters. And there we really are reliant on the isotopes or maybe additional chemistry to look for this. So some of the other things I think to point out as a community is when we correct this snow accumulation record, we correct it for compaction, densification, there's still some things that we're not quite so sure on, so not always completely accurate on how we calculate the thinning and the flow, for example. So it's just to point out that even with these records, we expect there will be quite a bit of noise, there's quite a bit of variability, and so sometimes just relying on a single record can be difficult. Having said that, so once all these things have been accounted for, we can produce our snow accumulation record. And this is the first snow accumulation record that I put together from the Gomez ice core. And so this is the annual snowfall in the dashed back line, and then I've got a running decadal mean through this. And this was quite kind of exciting when we first plotted this up, because it really did confirm that those the year that we were in the field and we had to do all that digging to retrieve the weather station was, you know, it was an exceptionally snowy year. And in fact, it was one of the snowiest years since 1850. And so when we looked at this record, it was really confirming that actually what we were seeing in the last decades of the 20th century were considerably higher. So actually double what we were seeing at the beginning of the record. So double what we were seeing during the 1850s. And so this was really exciting stuff. But actually, it really didn't fit with the general consensus from the community about what snowfall was doing. So there have been a number of papers and some sort of high profile papers. So the paper here from Andy Monaghan and others, where they'd concluded, they'd used ice core records and other stake measurements to conclude that actually, you know, not only that they hadn't seen this increase in snowfall, but actually that the snowfall change since 1957 was insignificant. And in fact, if you're looking at some of the figures here, you'll see it's actually showing a decline in snowfall. So this really didn't fit with what I knew was happening or what I'd observed, but it did fit a little bit more with...
Sorry to interrupt you, woman. There appears to be someone on the call who has not muted and they're moving around the desk. I'm not sure who it is, but if you could please just be vigilant to mute so that we're not interrupted. Thanks very much.
Thank you. So as I was saying, so it didn't fit with the idea of what was happening with snowfall, but it did fit with some of the other evidence that was coming out, particularly from the instrumental records that particularly the Antarctic Peninsula was getting much warmer. And then, of course, when Eric Steig came out with his warm underbelly story, you know, it all fitted together nicely, saying, well, actually, the atmospheric temperatures are warming. So how come the atmosphere is getting warmer, yet it's not getting wetter? So those two things seemed a little out of place to me. And it wasn't too long until there was another study following on from this, which again kind of went back to this old idea that the surface mass balance during the recent period really wasn't exceptional. So actually that it wasn't exceptionally high, and in this particular study over the context of the last 800 years. So this you know, kind of got me worrying. Was Gomez just an anomaly? You know, is it possible that you could have rising temperatures but snowfall showing no change? So through sheer stubbornness, and it took me a little while, but I kept going back and I managed to draw some more cores to try and build up this story of what was going on. And so I was able to replicate what we were seeing at Gomez at multiple sites across the whole of the Antarctic Peninsula in a transect, and really confirm that actually this is a robust and it's a regional story. There's definitely a big increase. But again, I mean, this was still just looking at the Antarctic Peninsula, but thankfully there was others as well, looking at other cores from around the continent. And so then the next kind of logical step for me was that, you know, I couldn't just answer this question with the data that I had. I needed to bring in as much other records as was available. So as part of the work that I've been doing with the Pages 2K network, we set about bringing together all of the published records. So this was building on some of the existing compilations, but we had the advantage now of being able to incorporate a lot more low elevation sites, and particularly all the new records that I've been collecting from the Antarctic Peninsula. So in this initial study, we managed to pull together 79 records that met my criteria of being annually resolved. They needed to cover a reference period, which we'd selected as 1960 to 1990, and they all needed to be corrected for thinning. So we used the published compilations, the published records for this. But unlike some of the previous compilations, what we were very keen to do was separate out the differences in elevation. So we really wanted to make sure that we separated out the high accumulation coastal zone from the low accumulation interior of the continent. And just a little note on the time span for a lot of these. So although we had these 79 records, some of them go back over 1,000 years, but only 49 of these actually cover the past 200 years. So there's a bit of a limitation in what we can do. But we took each of these records and we produced regional composites, and we were actually able to then weight them for the different area and then convert them from snow accumulation to surface mass balance by using the data from the regional climate model. So we used RACMO for this. And then when you put all of these regional composites combined and their area weighted, what we could actually see was a pattern more in line with what I had been expecting, which was this positive trend in surface mass balance during the 20th century. So the figures just here showing this is the total Antarctic ice sheet and the surface mass balance from the ice core records. So it's shown as the annual again in the dashed line, and then we've got the decadal average running through that. And for comparison, the red lines are the corresponding data from the RACMO model as well. The lines on here are just showing the annual average, and then we've got for this reference period, so 1960 to 1990, and then the standard deviations above and below this. So what we could see is that very clearly the recent trends that we'd seen during the late 20th century, early 21st century, were much higher than the average for the previous period. And actually the histogram here again is showing that both the 50-year, which is shown as the solid line, and the 100-year trend, shown as the dashed lines, were outside of the sort of range of natural variability. So these recent trends and this recent warming was unusual in the context, and in this case, in the context of the last 1,000 years. So in order to understand what was going on and really get into the detail about what's driving this, we needed to do a much better job and look at the spatial patterns. And this is where Brooke Medley's contribution was invaluable, in that she was able to come in and take the snow accumulation records and rather than just looking at these as time series, actually to effectively map these onto the spatial grid of the atmospheric model. So this really takes advantage of the high spatial variability in the model domain. But with the ice cores, we're then able to extend this further back in time so we can see how these changes occur. And so what we're looking at here is just the spatial variance. So we're looking at where the ice cores, so the areas in green, are where there's a really good high correlation between what the snow accumulation records are telling us and what the models are telling us. So there's really good spatial covariance between those. And so obviously there's areas of red in the map where we're approaching zero, and this is because we just don't have the data. So there is some limitations still, and clearly some areas that we need to be targeting for getting some more data in here. But the result of this work was that we've now got a spatially complete picture of how surface mass balance has been changing. And so again, we've selected this period from 1957 to 2000, and we can see the really strong mass gains, the really strong increases in snowfall shown here in the blues in the Antarctic Peninsula. And then we've got this dipole pattern where this is mirrored by a decrease in snowfall shown by the red in the area of West Antarctica around to sort of Victoria Land here. And this dipole pattern is a reflection of the very dominant role of atmospheric circulation in this region and the role of the Amundsen Sea low, which brings down all this warm, moist air to the Antarctic Peninsula. But conversely, these sort of strong winds coming off the continent are these cold and dry winds, which mean that the snow accumulation in this region is decreasing. And what's interesting to kind of note, so this was a really interesting and great pattern to show, but we actually used a very similar approach to the previous reconstruction. So for example, the work of Andy Monaghan and others, but there was a few kind of key differences. And the first was that with mapping this onto the reanalysis data, we were able to utilize the newer reanalysis products, and they themselves have increased in their spatial resolution, and they've increased the amount of data that they've been incorporating in terms of the observations and the satellites. And then the other really big thing was the inclusion of more records. So for our study, we had 79 records compared to the earlier one, which used 16. But of these 16, actually only 13 of these were from ice cores, and most of the records were very short. And only 3 of the records that they included came from a sort of coastal region under 2,000 meters of elevation. And as you can see, there's nothing there from the peninsula. The other advantage that we have in the kind of follow-up study, if you like, is that we had longer records. So we weren't just looking at these very short cores, we actually had records that span the full 1,000 years, but particularly for looking at the 20th century changes, it shows that this pattern is maintained over the last 100 years. So it's kind of a longer trend. And the headline really from this study was that being able to calculate the mitigating effect, sorry, my slide turned a bit quick there, calculating how much this has actually mitigated global mean sea levels. So what we can show from this study is that between 1900 and 2000, snowfall across the entire Antarctic ice sheet, and for this study included the peripheral islands as well, was mitigated by 1 millimeter per decade. So that's another way of thinking about this, is if the snow hadn't have fallen on Antarctica and become trapped there, global sea levels during the 20th century would have been 10 millimeters higher. And again, this kind of rate of change shown here for the total Antarctic ice sheet in the black, we can see this sort of acceleration during the latter part of the record. And in fact, this rate of increase, or this mitigating effect, increased to around 2.3 millimeters per decade after 1979. What's interesting is actually that looking here for the total Antarctic ice sheet, we can see that the dominant, the dominant contributor to the sea level mitigation is actually from East Antarctica. And this is the region that in previous studies, people had assumed there'd been a very insignificant change. But I think it's just important to remember that when area weighting these records over such a vast area as the Antarctic plateau in East Antarctica, it's only small, very small changes can actually build up and have a very significant impact on sea level. However, I need to put this one in just to say, although I'm very much the advocate that understanding surface mass balance and snow accumulation is really important, it's also, I do need to say that the snow accumulation gains are only accounting for around a third of the mass losses that we're seeing during the period from 79 onwards. So although snowfall is really important, we're in no means keeping pace with the mass loss. But it's important to just note here the differences in timescales. So the records that I've been showing you, I've been concentrating on changes over the last, during the 20th century, so we can go back over the last 100 years, but actually the ice cores, we could be taking this back much further. Whereas the records of mass loss come from our observational records, and those are very short, only within the satellite era, and in fact the data here just from 1992. So following on from this, there's been a number of other studies that have taken this ice core reconstruction and have been doing a range of different data assimilations and approaches to explore how the surface mass balance has been varying over the longer time period, so over the 1,000 years. And so showing here the reconstruction from the ice cores is in the black, and then the various ensembles from these global circulation models. And the models themselves have long predicted that there should be an increase in snowfall across Antarctica as it warms. But up until quite recently, there has been this mismatch, and it's that the observations couldn't replicate this increase. But now that we're finding we are getting closer to a consensus. So when looking at the two, there's clearly capturing this increase in snowfall during the 20th century, but there is a bit of a difference across the regions. So for West Antarctica, the reconstruction, if you can see, the black line is pretty much at the top end of what the ensembles would be producing as an increase during the 20th century. So suggesting that maybe the models are slightly underestimating in that region, or the ice cores are overestimating. But actually it's in East Antarctica. The models would predict a much more homogeneous increase in snowfall across the whole of Antarctica, whereas what we're seeing from the observations is that that's not quite the case. Now it's worth remembering. Yep.
Sorry, can I interrupt you on that? There are a few questions in the chat. There's a question from Gavin. Doesn't mass loss include surface mass balance already? That's IE Grace. I think maybe you were covering that.
Yeah, so when we're talking about the surface mass balance, so I think I put that right at the very first slide, but maybe didn't go into it. So we're talking, so surface mass balance itself is made up of, it's the contribution of precipitation or snowfall, but then it also takes into account the mass losses from sublimation or from melt or runoff. And across, you know, for most
yeah, sorry, that wasn't the question. The question was whether you were comparing it to total mass loss, but my thinking was that the total mass loss comes from GRACE, which obviously includes any changes in the surface mass balance as well, because it's the total mass.
Yes, yeah. So I mean that's very true. So it's difficult to differentiate between the two in this very short period. It's saying how much we've lost, but not necessarily accounting for how much we've. Yeah,
right, but if you got 78 from surface mass balance gain, but you've lost in total 218, right? Then that means that the anomalous mass loss from runoff and calving has to be 218 plus 78, right? Which is like 300 and something, right? Isn't that the addition?
Yeah. So right. Okay. So
yeah, that one there. Yeah.
Yeah.
Yes. So they're not balanced. Like, so the 219 includes the gain from the snowfall, but you've lost 219 net, which means that you must have lost like 300 in from anomalous mass flow.
So it's suggesting that there's actually a greater degree of loss than they're capturing. Is this, yeah?
No, I mean, it's arithmetic.
That's what I would have thought also, but I need to probably refer to the reference.
Oh, yeah, but I don't want to derail your talk. So sorry, carry on.
No, that's fine. Okay, so yeah, I'm just presenting what we're showing as how much this works out as how much snowfall has increased versus the published, you know, what mass loss has occurred at the time. So yeah, I'm sure there's probably going into the arithmetic there of working out the exact differences, but my point being that it's an equation and we're presenting one half of it. We've also got to take into account the other part of it. Okay. Was there another question in the chat that's not going to derail me so much? Or
we'll talk about it at the end. Johnny said he'll talk about he would like to ask this question at the end. We have a question from Jeff. So does the RACMO model show some spatial pattern in the change?
Does the RACMO model show a spatial pattern?
Yeah.
Probably have to talk to some of the RACMO people. I mean, certainly it captures the region, like the spatial pattern from coast and the different orographic signatures. That's what I showed at the beginning. But the RACMO doesn't, and the same way that the reanalysis doesn't. If I just go backwards, I don't know how far back I can go in here. So just looking at this one here. So from the reanalysis and you know, RACMO being incorporated in the reanalysis data, it doesn't actually show a very strong trend during this period. So I'm not sure if that's directly answering the question. It certainly picks up the spatial variability, but it actually doesn't show a strong trend. So just sort of showing, for example, here we've got a relatively low trend during this period from 79, whereas the observations are suggesting it was much higher.
Yeah, that was the question. I think does RACMO show the same spatial distribution?
Okay.
Sorry for derailing you.
Okay. Remember where I got to now? Was I here? Right. Okay. So it was just sort of my you know, when entering into the kind of modeling domain, I'm not a modeler, and so I don't want you know, I have to remember that the models have an incredibly difficult, you know, it's quite a challenge that modeling surface mass balance presents to the modeling community, because it's highly, you know, surface mass balance, it's highly spatial, seasonal, and there's interannual variability to take into account. But what the reconstructions have been able to do, and this is something I'm really pleased about, is that the reconstruction has been used to help evaluate the models. And so I'm just kind of highlighting some of the work here. So this is Tessa Gort's work, where they've actually used the reconstruction as the sort of truth, if you like, to produce a scorecard for the GCMs, for the global circulation models. So what they're showing here is that if you can just see that the darkest kind of indigo line at the back is the reconstruction, and then they've got the different ranges of uncertainty above and below this. And so a high ranking model is one that you can see in the middle that pretty much sits over top of the reconstruction. And so that's within the bounds of expected variability, versus a lower ranking model, which actually sits right outside above the 3 times uncertainty level. And so this is really useful because they've been able to then rank the top, I think the top 10 models, and use those to actually reduce some of the uncertainty in the predictions for 21st century changes in surface mass balance. So, I mean, it's great that the reconstruction has been used in this way. I mean, that was always the intention. And some of the things that we say is that we're going to produce this and it's going to help the models and it's going to help future predictions, but actually it has been used in this way. And so that's really good to see. But some of the other things in which that we need to perhaps reduce the uncertainty is our understanding of the drivers. And I still don't think we really have this very well understood. So essentially what we want to know is, you know, why is it that we're seeing these increases in snowfall and this different sort of spatial pattern? So I'm just going to go right back again to sort of the personal journey here and bringing this back to the Gomez record. And so we actually went to that site specifically to pick out a record that would capture changes in the southern annular mode. So we chose the location based on that. And indeed, we found that the snow accumulation record was highly correlated with the SAM index. And we estimated that 28% of this increase that we saw since 1957 was actually related to the positive trend in the SAM at the time. And then we jump forward 10 years, and the work that Brooke was able to do is actually look at this on a continental scale and conclude that, in fact, 80% of the regional variability can be explained by changes in the southern annular mode. So these are the 2 reconstructions on the left for the 100-year and for the second half of the 20th century, and then looking just at what the SAM component of this is in plot C here. But what's interesting is that the SAM, although it can explain this spatial pattern, it can't actually explain the trends that we've been seeing in the snowfall, because actually the observed SAM trend would have been accompanied by a decrease in accumulation during this time. So this can't explain what the increase was. So if we extract the SAM picture from this, the SAM signal, what we're left with was this residual in the final plot here. And this is really showing the underlying trend of an increase in snowfall that is in some ways much more similar to the way the models were capturing this, and that it's a much more homogeneous increase. So definitely there's more still around the coast and in the peninsula, but actually there's increases across the whole of the Antarctic continent. And in fact, these is trying to understand really what's driving this increase that's important. And in fact, just a warming atmospheric surface temperatures can explain some of these warmings. So it can explain the increase in snowfall that we're getting. And so it's relatively small changes in temperature is enough to create these trends. So some of the other things that have been proposed, so ozone has been proposed as a driver for the increased snowfall. So this is some of the work that Jan Lennertz has done, where they were using the reconstruction from the ice cores and then comparing this with the community Earth system model, using simulations where there is an ozone hole prescribed and simulations where there wasn't. And this suggests that there's the big increases in precipitation that we see can be attributed to ozone. And it's just important to see really that the spatial pattern that they produced from this study really resembles the spatial pattern that we saw from the reconstruction. Some of the other things just to kind of touch on quite quickly, but other things have linked changes in surface mass balance to changes in sea ice. And this is particularly some of the work by Yetang Wang in focusing just on West Antarctica. seems a fairly clear link because we know that we've got these big changes in snow accumulation around this region, and then in the adjacent oceans we've got these very big changes in sea ice, so particularly big declines in the Bellingshausen Sea. So this suggests that there's something going on with the sort of availability of moisture as you're removing the sea ice. But one of the things that's really difficult for us is that changes in sea ice are also dependent on some of those other changes. So changes in the winds, and which themselves can be attributed to changes in the southern annular mode or ozone, or changes in temperature, and not to mention all the huge amount of influence from the sort of tropical teleconnections, changes in modes of variability. So there's essentially an awful lot going on, and sometimes it's not quite so easy to disentangle it. But not only that, when we start looking at the drivers, what we see is that many of the drivers that we're using to explain this increase in snowfall are the same as the drivers that we're talking about for what's driving the mass loss and the melt. So just jumping to the melt story, if you like, and I'm just showing here particularly these red areas. You know, we know we're getting a lot of melt, particularly from the West Antarctic region along this Amundsen Sea coast. And a lot of this melting has been attributed to changes in basal melting. So we've got this increase in relatively warm circumpolar deep water that comes up onto the continental shelf. And the process by which this has been happening has in many ways been attributed to changes in the winds. So some of the ideas for how the winds are related to this include a southward displacement, so it's a shift as the winds get closer to the continent, although my understanding is that that's actually still quite difficult to see in the instrumental records. Other suggestions are that it's an increase in the strength that's driving these processes and upwelling, or also that it could be a weakening, so an increase in strength of the westerlies versus a reduction in the strength or a weakening in the easterlies. So therefore, it's really obvious that the winds are playing a very important role in driving the variability, not just in the melt side of the story and the mass loss, but also in the mass gains and in the snowfall side of the story. So while we've got the ice cores now that we can produce these reconstructions of snowfall, we've got the fantastic remote sensing and observations that can look at the changes in mass loss. What we haven't got is a really good long-term record of what's been going on in the winds. And so this is where I want to kind of highlight some of the other things that ice cores can do, which will hopefully help us address some of this lack of understanding. So the easiest thing to think of is it's really important to remember that anything and everything that you see in a polar ice core comes from somewhere else. So everything from the snow itself, the composition of it, the chemical impurities that it contains has come from somewhere else and been transported, whether it's a local source or a long-reaching, long-range source. It's all been transported there. So in some ways, all of the proxies that we have in an ice core have been influenced or will be dependent in some way on changes in circulation, atmospheric circulation, and changes in the winds. So obviously changes in source are going to play a role, but the winds and circulation are always going to be in there. So just looking again at this very simple kind of conceptual model of mass balance. So this is again where we're looking at the snowfall coming in. We have snow coming in, where we could also have melt going out, sublimation. There's all sorts of other things at play, looking at the flow. And these are all influenced by changes in oceanic conditions, atmospheric conditions, evaporation, and the winds that are driving these changes. But for these processes, we have a range of different means of observing this during the recent period. So from 1979 onwards, we've got the satellites, we've got weather stations, we've got observations. But what about when we want to go further back in time? And so this is where the ice cores really come into their own, because the ice cores contain a huge amount of information from the marine domain and from the sort of terrestrial environment. So marine aerosols, ice cores contain a lot from the sea salts that could be arising from either bubble bursting or wave breaking, or from the surface of the sea ice themselves. All these marine aerosols can be transported to the ice core site. Then we've got the mineral aerosols, and these are the continental species, so the dust that's come from the southern hemisphere land masses and been transported, often very long range transport. But then we have a huge amount of other biological processes that are taking place. So changes in productivity, which themselves are connected to changes in wind circulation, particularly changes in sea ice that's driving these, this biological pump. And a lot of this produces organic aerosols, which until very recently were quite hard to detect in Antarctic ice cores. But now we've got quite a lot of advances in our methods. And it's actually shown that these show a lot of potential, particularly in coastal and island sites. And then finally, the snow itself, the stable water isotope record. So this has long been used as a proxy for past surface temperature, but it also tells you a lot of information about the source conditions and the transport to the site. So for the final part of this, I'm going to summarize a couple of the projects that I've been working on, where we're trying to reconstruct changes in winds and circulation that will ultimately help us understand what's driving Antarctic mass balance. So the first one I'm going to look at is marine diatoms in ice cores. Then I'm going to switch to a sort of more traditional approach, looking at the isotopes, and finally a step towards a more continental reconstruction. So starting with the diatoms, this is some work I've been doing for the last few years, where we have found marine diatoms in ice cores. So marine diatoms are these unicellular algae. They're in all of every water mass across the globe. But for us, they're uplifted off the surface of the ocean by strong winds, and then they're transported to the ice sheet, where they become deposited and then buried in the snow. And for us, this provides then a really fantastic record of past wind strength and also direction. So very simply, stronger winds means more diatoms that we see in our record. So the potential for this has been recently demonstrated. So Claire Allen's paper from last year was showing that there's a really strong correlation between the amount of diatoms that we get in the ice core at the Foligno site and westerly winds. So we can see these are the plots in the bottom here. And this work has now been investigated at a number of new sites. So we've had a fantastic PhD student, Dieter Tetzner, and he's really taken this onto a new level. So he's been exploring, showing that this signal is robust across multiple sites. And then really interesting, working together with Claire, they've actually been able to identify down to species level what we're seeing in the core. So it's not just about how much we've got, it's actually about which species. And this is really interesting because this is going to help us to differentiate between not just wind strength, so things getting more diatoms just because it's got windier, but actually a potential shift in the circulation pattern as we start to see new species emerge. So I'm only going to touch on this because this is Dieter's work and it's coming up. There's some papers published at the moment and there's more coming. But we've got a really exciting new record which spans the last 140 years. And what this record is able to show is that not only do the winds get stronger during the end of the 20th century, but actually by using this species assemblage, we're able to quite clearly and definitively locate the point at which the westerly winds and this wind belt actually shifted south. So that's a really excited, and it appears to be quite unprecedented in the context of the last 140 years. So please look out for that work coming soon. Now, the diatoms are very much a new proxy that we're working on, but there's also still things that we can do with the more traditional proxies. So the stable water isotopes, for example, is something that we've widely used, but there's still a lot more we can get from it. So I'm currently working on a new record from the Antarctic Peninsula. This is with my postdoc, Daniel Emanuelson, and this is from Palmerland in the southern, this is just kind of so you can get your eye in on here, sorry, Antarctic Peninsula, South America up here, and the ice core is just here. And this record actually goes back 400 years, so it provides one of our longest records from the Antarctic Peninsula. And what we're showing here is the correlation between the stable water isotopes and the surface air temperature from era 5. So the red region here is showing a really strong positive correlation. And what's relevant for this particular talk is how strongly correlated the isotopes from this ice over here are with the surface temperatures across the ice shelves. And one of the reasons for this is because the ice core is actually capturing changes or capturing the circulation, if you like, so that the isotopic signal that we're seeing in the ice core is reflecting this warming that's going on here, and it's reflecting these warm winds that are coming over the north of the peninsula or around the tip of the peninsula here. And so this has been linked very much to ice shelf collapse. So we know there's these Fuhn winds that are influencing, but also surface air temperatures are driving melt on the surface of the ice shelf, which then ultimately lead to its collapse. So what we're able to show here is that potentially we've got an ice core that's capturing what's going on. So not just capturing the surface air temperature over the ice shelf, but actually capturing the changes in circulation and tracking what the winds have been doing. So if we now look at the full record, so this is our 400-year record, we can see that there's this clearly, during the latter part here in the green, there's clearly this warming trend that we know from the instrumental records. And this we're assuming is also suggesting that there's been this warming across the ice shelves, so not just at the ice core site, but also across the ice shelves. And then during these, and this is when we feel that we've got most of them melt. And then just looking further back in time, we can see that this isn't really, you know, although this does stand out as quite a significant period, there have been periods of warmth in the past. There's been full periods and periods of warmth. And so it's fair to assume that there may well have been melting across the ice shelves prior to the sort of collapse during the 1990s. In fact, when we compare our report with some of the observed melt lenses, so these are from boreholes taken from the Larsen Sea ice shelf, they are observed melt layers, but they've got modeled ages. So they've used the ice flow models to estimate when this melt event occurred. And these correspond quite nicely. So this is from a paper by Bevan et al. In 2017. But actually the periods where we get relatively high warm periods in our ice core correspond with when we've observed these melt lenses actually on the ice shelves. So this is a really interesting kind of approach to maybe think about using an ice core from a continental site to actually reconstruct what's been going on the ice shelves. And the final thing that I'm going to just quickly give you a glimpse into is a new compilation that I'm working on to try and produce more of a continental reconstruction about what's been the changes in sea ice and atmospheric circulation. So in much the same way as we collated all of the snow accumulation records, this is some more work that I've been doing on behalf of the Clivash 2K working group that I lead, where we've been compiling sodium and sulfate records from all the available ice cores. And you can see all the ice cores here with their relative ages. And the reason that we've picked sodium and sulfate as opposed to the diatom record, which I've just shown you was looking fantastic, is because that's still very much a work in progress and a new proxy, whereas sodium and sulfate are readily available. So all of the different ice core groups that have produced data tend to be measuring the major ions and using them in dating. So it's readily available. And actually, when we had the call last year for data, we had a really positive response from the community. With 111 records submitted, so much more than we'd seen from the snow accumulation record. And so we're now working on this data compilation, and the idea is that hopefully we're going to get to a position where we can produce similar kind of regional or spatial pictures as we did with the snow accumulation to overlay what's changing. And this is just, so as we're working on this now, this is just to give you a bit of a glimpse of how this looks in terms of concentration during the satellite era. So these are the concentration, the amount of sodium, so salts in the ice cores during this period from 1979 onwards. And so hopefully give you a bit of an idea about how we can then use this and hopefully in the same approach produce a gridded spatial map of salts across Antarctica. So that's the end. That's just kind of my conclusions, in that I hope I kind of gave you a bit of a run through again, and I'm aware some of you maybe have seen it before, but understanding how snowfall and snow accumulation from ice cores can be really, really important in our understanding of Antarctic mass balance and its contribution to sea level rise, but also that ice cores are much more than just snowfall. And so there's a huge amount of other proxies out there that we're working on that will hopefully help us to understand what's really driving these changes. And with that, I'm finished. Thank you.
Thanks very much, Liz. That was fascinating. So there were a couple of questions in the chat going along, and then we'll probably open it up. If you would like to ask a question, feel free to raise a hand via Zoom, or you can also just speak out. So, Johnny, any chance you'd like to unmute and ask a question?
Sure. Hi, Liz. Thanks for
Johnny, nice to see you.
Nice to see you. I have a couple of questions now, but I didn't ask my one earlier because it's kind of regional. But I was going to ask about those very bright blues and bright reds in your red-blue map of change in accumulation rate, and in the area of the coast of Mary Birdland. And I was wondering how much that contributes to the total, just because they seem like such large signals. And then how well are they constrained by cores? And I guess there doesn't seem to be many cores in that region. And would that be a good place to do an ice core?
Ah, I thought that might have been a leading question. So sorry, just let me look in here. Yes, I mean, it's the way that you can just see underneath here. Perhaps if I go see the one, take the yellow dots off, you can just about see where we've got the cores in the grey dots. So obviously we've got some regions where we've got cores, we've got some bits that we've got hardly anything. And so here we really are relying on what the spatial pattern from the reanalysis data. But yeah, I mean, there are some quite significant kind of differences and quite significant changes, and in some places, I mean, for me, it'd be looking along this area of the coast and kind of Johnny Maudlands, where we clearly don't have very much, and there's a huge amount of differences you have. So some of these areas I think are particularly interesting, but yeah, certainly there's where was it you were interested in?
Oh, sorry, yeah, am I getting the right region? So just along from Thwaite, so round towards Roosevelt Island, just the coastal area, here, whatever it's called. Maybe it's not even the right name. Yeah, so those very dark, very large negative trends, do they contribute significantly to the overall
I mean,
sea level rise?
Yes, we're talking, I mean, these are showing up as quite, sort of dramatic. The losses here are similar to the increases that we're getting across the peninsula. So they will be having, sort of balancing each other out or not. But this particular region is really interesting, and that's why it would have been fantastic if we could have, as part of Thwaites or something, got some ice cores along here, because along some of these coastal domes would be an absolutely perfect place for a record that would give us a good indication, because we just don't have very much. So I do have a new core from Mount Cycle. I think that's just about there, but it's only short. So it's one of the ones we collected a few years ago. So it only goes back 25 years or something, but that's showing that is capturing, the variability, and it's proving that the reanalysis data is doing a good job just within that short time frame. So I think there's real potential to go back and get longer cores. Trouble is, it's a difficult place to get to.
Yeah, absolutely. Thanks. Yeah.
Thanks, Johnny. It's good to see you. So we have also Jeff has got his hand up. Jeff, would you like to?
Hi, Liz. The salt and precipitation can tell you something about cyclogenesis, can't it? So if many of the cyclones are generated from gravity waves over the Andes, and if that wind jet shifts, then you'll get different cyclogenesis produced, and the storm tracks will change. So is the salt telling you something about that?
Yeah, so I mean, like I said, everything. So I mean, often we look at things in these kind of large scale modes, and actually what we're really referring to is the more kind of synoptic changes. It's these low pressure systems, these cyclones, and these individual storm events that are bringing everything in. So there are some limits to what we can do with the ice core, because a lot of the records that we have are only looking at annual. So it's difficult to get down into the kind of differences in storm variability. However, some of the cores that we have, particularly the really high accumulation ones from around the coast, we can get down to definitely sub-seasonal. And there has been some work. So I've done some work with Scott Hoskins, actually, where we're tracking the different storm events, individual storm events that were coming into a particular ice core site, and able to kind of differentiate between those. So there's definitely something in it. And that's one of the ideas, is that producing these databases is, if I can help by compiling all the records that we have, then that means they're open to the community. And, hopefully that's kind of open to, new methods, AI, machine learning, different approaches where people could really take to explore this data.
Okay, thanks.
Do we have any questions from the group?
I had a question. I think it was mentioned that there was some connection between the ozone levels and precipitation. Could you please explain that a little?
Yeah, so I was actually presenting some work by Jan Lenitz on that. Let me just see if it's easy to see on here. So I think this kind of link between ozone is the relationship between the ozone and how this has influenced the polar vortex and changes in the winds and circulation. Sorry, I'm just trying to get to the right slide. Yeah, so this, so if you're interested in this isn't my work. I was just presenting how the record's been used. But they were effectively using the model in two different ways to show that without the ozone hole, you couldn't replicate the spatial pattern in snow accumulation that we see from the observations. And so I think this is linking to changes in the winds as a result of the ozone. But I think if you want more on that, it's probably best to contact Jan Lenitz directly or check out the paper that I've got on here.
I see Gavin has his hand up. Gavin, would you like to unmute?
Yes, hi.
Hello.
How are you?
I'm good, how are you?
Yeah, you know, not too bad.
I get nervous when you ask a question.
Why? Nice. So I was gonna. I was actually kind of following on from Vivian's comments, and you made some comments about what the models show and things, and I was just, you know, while you were talking, I was looking back at you know, what our models showed, you know, 15, 20 years ago. And one of the things that they were very clear on was that the ozone hole was causing and would continue to cause increases in the southern annular mode, pushing it towards a more positive phase, which it has happened in quite a nicely predictable way. And then, you know, and we looked at, I had it here. Hold on, where did it go? Where are you? Where are you? Oh, okay, I can't find it anymore. Anyway, but we looked at a number of things. I think including temperatures, which, you know, and the temperature signal from the southern annular mode increasing is slight cooling in the center and slight warming on the peninsula. And we also, I'm not sure if we looked at accumulation, though it might be interesting to go back and have a look at that. But we also looked at the signal in water isotopes. So we had, you know, water isotope patterns associated with the southern annular mode, which I think, you know, when Eric did a compilation of relatively recent 018 cores, it showed a very similar pattern. And so the point being that I think the models, you know, they historically they've had, you know, difficulties with, you know, the climatology of sea ice and things like that, right? And so, you know, some things don't look quite right. But some of the trends, even for models that were run, you know, 20 years ago, they seem to capture a lot of the phenomena that you're talking about here, right? And so when you say, okay, the models are doing this, the models are doing that, I mean, like, are you being specific about what the models show, or do you have something else in mind?
No, so I think what you're saying, and again, like my kind of introduction on this was that actually we knew from the models that we should have been seeing this increase in snowfall, but all the publications that were coming out at the time and the kind of consensus from the ice core and the glaciology community was that actually there was no change. And so that's the bit that got me, that we were at odds. We were at odds of what the physics says in that warmer should mean wetter. So we had evidence of warmer, but we didn't have evidence of wetter. And so I think that it's not suggesting that the models were getting it wrong. It was actually suggesting that, you know, in many ways, the models had the basic physics right and were picking up that we should have been seeing it. But it's taken until now, or a few years ago, as I'm aware this is already a few years old, to actually be able to, for the observations in some ways, to catch up. And you know, however much we kind of do it, I think I do think it's always going to be important that whether we're doing models or data, that the two of them come together. And so that's what's
right.
you know, so useful, is that actually in this case it's the data that's taken time to catch up, but now we have. And you know, so now we are picking it up, but there are still differences, I think, in certainly the regional models. And again, there's some work by Jan and others looking at the reanalysis data on a regional level. I think they're doing an absolutely fantastic job at picking up all of the detail, and especially the sort of newer reanalysis and the, you know, the higher resolution. They really are picking up these changes, but I guess maybe the global models are going to always find that a little bit harder. But yeah.
Well, I mean, but your attribution, you know, you're not saying, you know, there's a big component from, you know, changes in ENSO, which is affecting the Amundsen low. You know, you're looking at these long-term trends, which is the kind of things that the global models should be capturing, right?
Yeah.
Yeah. So I mean, have you looked at you know, what the latest models kind of show in terms of snow accumulation? I mean,
well,
I mean, it might
this
be
is some of the work that so this has been working with Goose and some of his groups. So this is showing what the models have been showing during the historical period. So this is the sort of historical
right.
During this bit.
Okay, so those are CMIP5 models, which are a little bit out of date and have, in general, pretty bad Southern Ocean climatologies. The CMIP6 models, which, you know, I know it keeps on changing and we keep updating
well, I think
everything.
One of the points then from the work that Tess has just done, they were looking at the CMIP6, and one of the conclusions from that was actually there isn't a significant difference between.
Well, you know, that also.
So I'd have to. I'm a bit of dangerous ground to remember exactly what it is, but whether there was actually, you know, in some ways, some of the ones were actually doing a worse job second time around. So I'm kind of aware of the models changing and trying to follow that. But so there has been various studies that are using the different versions. Yeah, but I think that's what kind of some of these studies are doing, is really trying to evaluate. We're evaluating both, aren't we? We're evaluating the reconstruction and the model.
Well, yes. I mean, it's only when they all match up when you have some kind of confidence. No, if they're different, you just basically at square zero again.
Yeah.
Okay. Well, thank you very much. Great talk. Thank you.
Thank you. Hello.
Well, I could ask another quick question. I think Craig's muted, but yeah, I mean, going back to thinking about the reconstructions, I think some of the corrections you talked about, fan corrections and ice flow corrections. What's the feeling in your community about those corrections? Are they kind of done and dusted in a way, and we have that pretty much okay for our purposes, or is it still, there could be qualitative changes to the results based on improvements in the fern correction, for example?
Yeah, I would say no. So I kind of highlighted those at the beginning of things that I still think we need to do a better job on. And I feel like I need to do a better job on, because when I'm looking at the records, especially some of these, you know, they're relatively shallow, we're talking 150 meters. And so there's the, you know, using just the kind of very basic like Nye model of assuming vertical, you know, that thinning is going to be the same as burial. And so I think that's outdated, but I don't, for each of these cores, have a better approach. And in lots of the cases, you know, it's great if all of these ice cores were accompanied by a geophysical survey. You know, that's the goal, that's the idea that should be with all of these, but most of them are not. And so most of them is an ice core, but we don't have very much information about what's going on around it. We don't know what's happening up and down slope. We don't know, you know, some of these kind of changes. So yeah, I was to say there's still an awful lot that needs to be done. And, you know, if someone had the time and the will to do it, it would be really interesting to go back and look at these records from scratch and actually do the work again to check that the that the thinning and corrections were actually appropriate, because that can make quite a big difference.
Well, we should talk more then, because it's certainly in our kind of wheelhouse, that kind of going back to those records and doing those thinning corrections is something we've been thinking about.
Oh, well, please do. I've got the data. I just need someone to help me understand a bit more about that. Yeah, because obviously the geophysics isn't my area. And that's why I think we definitely need to be working more across the community to kind of help each other out, really. Okay. So, yeah, definitely. Let's talk more, Johnny.
Laurie? Sorry, I was muted before, so I missed.
Yeah, that's okay. This is a really going back to basics question. When you're calculating annual mass accumulation,
yeah,
does it get harder to do? Are the errors larger while you still have firn rather than solid ice?
No, so it often gets harder the other way. So in the top part of the core, I suppose when you're in the firn, assuming you have an understanding of the densification processes, which I suppose, as we were just talking about, maybe, yeah, is still a bit uncertain. But normally when we're calculating the snow accumulation in that section, we've got, that's the highest resolution chemical records that we're going to be using to date it. What often gets harder is as we go deeper, as the annual layers become compressed, the data resolution isn't sufficient enough to detect these annual layers. I think that's when greater error arises.
So what are you're measuring the mass not by the density and thickness, but by accumulation of something else?
So we're measuring the accumulation of snow, but we do this by looking at the distance between annual horizons. And that marker of annual horizons becomes harder for us to see as we go further down and the layers become thinner. And then the data resolution maybe isn't good enough for us to be able to pick up these seasonal cycles. And for some of the species, so for example, I showed the hydrogen peroxide, that's fantastic in the top part of the core. And in some places it's brilliant down to 150 meters. But in other places, you might lose that signal within just a few meters. And so then you haven't got such a good seasonal cycle as you go down. So that's why lots of the ice cores we have, they're actually much older ice cores, but the snow accumulation records are relatively short because we couldn't annual layer count much further back. So I'm not sure if that's answering your question, because I guess you're maybe more interested in the surface processes. But one of the difficult things as anyone who works here will kind of know, is measuring the density in that real firn is quite tricky, because when you've got your ice core, it kind of crumbles away from you when you're in the really surface bit. So
well, that was my question really. If you have a meter between annual layers, but you don't really know the density very well, then your accumulation has that uncertainty with it.
Exactly. Yeah. So then we're working on a kind of modeled assumption between the data and between the density, and that's certainly something that we don't have that many measurements of surface density, and it would be quite useful to increase that and actually understand, how big the variability is. And just on a very practical level, it's quite hard when you're working with an ice core that's quite crumbly in the ferny layer, to get a really accurate density record.
Right. And, my interest is that it's the altimetry, the effect on the altimetry that is the real issue. And it'd be nice to know those numbers better. Yeah.
And I think, again, that's another area where a lot of the ice cores will have those kind of records of surface density that maybe aren't published or available. Is it the sum up? I think there is some means of trying to collect the density records, but that I'm fairly sure that there's a lot more out there that people have and could make available, which would be really helpful for the altimetry.
Okay, thanks.
We have another question from Olga. She's asking, how would geophysics help with the firn? How does geophysics help with the firn? Olga, would you like to?
Was that how would geophysics help with a firn?
Yeah.
She says, well, I guess just in our kind of understanding of the firn processes and the compaction. So I know there's been some studies, it's quite a long time ago, the kind of compaction studies and coffee cans. And actually the original site we went to at Gomez, there was a study by Rob Arthur doing these kind of coffee can and compaction studies, but they're quite limited. So it's just a sort of understanding. I guess it goes back to the previous question as well. It maybe in a measurement approach, maybe there's better ways in which we could bring in, you know, measure the density within the fern. Yeah, there's certainly some scope for technology rather than it just being us literally taking samples and weighing and measuring them. Perhaps we could be doing more sophisticated approaches.
Do we have any final questions from anyone? We're a little bit over time here, so we should probably let people go and get on with their day. I've got a final sort of question, I suppose. Do you know if there's somewhere where one might be able to access? Previously, you showed the planned view of Antarctic precipitation changes based upon your work. It'd be really interesting to overlay that with, say, for example, Grace. And so you could say, for example, around the Munson region, you might expect. I'm personally really interested in what's the mass flux to the ocean. And so to do that, I would have to subtract one from the other. And it looks like in some regions, it's amplified.
Yeah, I mean, all the data. Yeah, I mean, if the question is about data availability, yeah, all the data is available. So the original ice core data is all on the Polar Data Center, but you can find that through any of the links in the papers, but I can send it to you. And then Brooks data is also stored as NetCDF files, all ready to be used and has been used quite a lot. So yeah, it's all there and available.
Great, thank you. Maybe I'll bother you offline.
Yeah, yeah, that'd be good.
Okay. So we should probably close off then here. Thanks everyone for joining us. Thanks again, Liz, very much for a fascinating talk. And I hope you all have a great rest of the day.
Brilliant. Thank you. Bye.